When you're solving exponential and logarithmic equations, you're going to use a few basic principles. For example, if you have x plus 3 equals 12, this is just a normal equation, but what would you do to solve it? You'd say subtract 3 from both sides. Why would you say subtract 3 from both sides? Well, clearly, you're adding 3, and the inverse of adding 3 is subtracting 3. So just like how adding 3 and subtracting 3, in other words, addition and subtraction, are inverses of each other, we also know that multiplication and division are inverses of each other, but we also know that an exponential and a logarithmic function, that these also represent inverses of each other. I know I use 3 here, but it doesn't matter. We can use anything other than 3 and it would essentially work out to be the same. So in much the same way that these eliminate each other, and these eliminate each other, and these eliminate each other, basically any combination of these two, an exponential and a log, will eliminate each other. For example, let's try a different base. Let's suppose that we had 5 to the x and we had log base 5 to the x. We know that, or of x, we know that these functions are inverses of each other. So no matter how we combine them, they're always going to eliminate each other. So if we combine them by doing log base 5 of 5 to the x, then the log base 5 and the base 5 are going to cancel each other out and just leave x. Or if we did it the other way, 5 to the log base 5 of x, these would similarly eliminate each other and just leave x. So what are some other principles or main things that we need to think about? Well, the example that we had before showed that basically if we had an exponential by itself and a log function by itself, then we could either, in this case, exponentiate, that's when we write a large base at the bottom to cancel it out, or we could apply a log to cancel this out. But the basic principle, the other basic principle is make sure that what you have is by itself first before you start exponentiating or before you start applying a logarithm. So let's do a quick example. We're not going to work this one all the way out, but we want to see, again, a basic principle that we can use. So suppose we had a problem, natural log of x plus natural log of 5 equals 3. What do we think we should do? Well, some of us might go straight to exponentiating, and we'll say, oh, put a base of e on both sides. And then some kind of way we might end up with x plus 5 equals e to the third. But this would be incorrect because our exponentiation, we're not really sure. Does it go to this natural log, or does it go to this one, or does it go to both of them? So just so we can be sure, and let's rewrite the problem. Just so we can be sure, what we would want to do is to make sure that these two natural logs combine into one natural log. We're going to condense it first. So we use our log properties such as log x plus, log of x times y is equal to log x plus log y. And we say that because we're adding, that means that we're going to take the two arguments and multiply them under a single log. So in this case, we would multiply the x and the 5 under a single log. So this is what the new problem would look like. Now it's ready for exponentiation, but the main idea is make sure that you get whatever you're going to exponentiate or take a log of by itself. So another example, this time let's do an exponential. If I just had 3 to the x equals 5 and I needed to find an answer, well, this is ready for me to do some inverse operation. In other words, to apply the log base 3 to both sides. But what if the problem said 3 to the x times 4 is equal to 20? Well, then we still need to get this 3 to the x by itself. So we would have to divide both sides by 4 first before we even think about applying any kind of logarithm. So keep those principles in mind as we work the following problems. To solve this equation, notice that we already have log by itself. So what we're going to need to remember is how are exponential and logarithmic functions related to each other? Well, remember that 5 to the x and log base 5 of x, these are inverses of each other, meaning that when we combine them, they're going to cancel each other out. So as an example, log base 5 of 5 to the x would just simply leave us with x. Or if we combine it the other way, 5 to the log base 5 of x, these would cancel each other out and just leave x. So we're going to use that to our advantage. What we're going to do is we're going to use a process called exponentiation. Basically, all it means is take the base that we have here and write it on both sides. So we're going to use a base of 5 on both sides. So remember, base 5 and log base 5, they're going to cancel each other out. So now we have x is the same as 5 to the negative third power. But if we remember how our exponents work, 5 to the third power is 125. So 5 to the negative third power just means put that under 1. So it'll be 1 over 125. So that is the answer for this question. We're also going to need to exponentiate on this problem as well. So we're going to eliminate by exponentiating with a base of 4. Remember, base 4 and log base 4 cancel each other out. So we're going to have 3x minus 8 on this side and x on the other. So using normal algebra, we're going to solve by subtracting 3x on both sides. And then we have negative 2x is equal to negative 8. If we divide both sides by negative 2, then we end up with that x has to be a positive 4. We should check to see if this makes sense. Remember that the argument of a logarithm will always have a positive value. So this will always be positive. If it isn't, then our log does not make sense. So we're checking to see if 4 really is the answer. And if it isn't, we will say there is no solution. So let's put this 4 back into first the 3x minus 8. So we have log base 4 of 3 times 4 minus 8. This is log base 4 of 4. So 3 times 4 is 12, and 12 minus 8 is 4. So clearly, this will work because we have a positive argument here. We also need to try it on the second part, on this particular expression here. So if we input 4 there, we know it also works. And so our answer is is x equals 4. So keep in mind, if we end up with a negative value here or here, then our answer is not a solution. This problem is a little different. What we need to do is we need to condense everything on this one down to a single logarithm. So notice that we have log minus log. Remember from what we said before that if we have log minus log, that it condenses down to the log of a quotient. So what we're going to say is that this side has to condense down to log base 2 of a quotient. the numerator is going to be x minus 3, and the denominator is going to be x plus 2, and that's all equal to 3. So now it looks a lot more like the problem that we just did. So how would you answer this? Pause the video, try and see if you can come up with the answer. All right, so what we would need to do is to exponentiate. So we're going to use a base of 2 because that's what we already have. And we're going to do that on both sides. So this base 2 and this log base 2, they're going to eliminate. So that leaves us with x minus 3 over x plus 2 equals 8. Of course, we can get rid of the denominator by multiplying both sides of our equation by x plus 2. These would eliminate. Now we have x minus 3 is equal to 8x plus 16. Basically, do our algebra. We're going to subtract x on both sides. So we end up with negative 3 equals 7x plus 16. And we're going to subtract 16 on both sides also. And we end up with 7x equals negative 19. Divide both sides by 7. And so x equals negative 19 sevenths. So we should check if this is a solution or not. Notice that if we put this value in here, what would happen? We would have log base 2 of negative 19 over 7 minus 3. But when we finish the subtraction, we'd have a negative number. So remember, this cannot be negative. It always has to be positive. So what does that say? That means that what we have here is not a solution. So we're going to say that there is no solution. Pause the video, try and see if you can come up with this answer yourself. So what we would do here is we would need to condense this down to one natural logarithm. So our log rules again say log x minus log y has to equal the quotient of those logs. So we're going to get this part here to be natural log of x over 3. And it's still equal to 5. What we need to remember is that natural log is the same as log base e. So natural log has e to the x as its inverse. So in other words, this is the inverse of log base e to the x, just like 5 to the x is the inverse of log base 5 of x. And so they would cancel each other out. So what that means is that if we combine these, however we combine them, they're going to eliminate each other. So in other words, natural log of e to the x would just be x, or e to the natural log of x would just be x as well. So if we're going to solve the equation that we have on the left, we're going to need to exponentiate with the right base. So we're going to exponentiate with base e. So the e and the natural log cancel each other out, and we're just left with x over 3 on the left and e to the 5th on the right. E is like pi, so what we're going to do is we're just going to leave it alone for now. If we really need to, we can estimate its value as 2.718 and work it out, but we're just going to leave e in here. So to get x by itself, multiply both sides by 3, and so x is equal to 3e to the 5th. We should check if this makes sense. Since this is positive, that means what we put here is going to be fine. Putting 3e to the 5th is going to be fine because we'll have a positive argument. So we've confirmed that this is the correct answer. That is the solution. Now we have an exponential. The basic idea, just like how we got the log by itself and used an inverse, The basic idea is going to be the same here. Get the exponential by itself and find the inverse. So that means that this 10 has to go. So we have 6 to the x is equal to 37. So what's the inverse of 6 to the x? Well, the inverse of 6 to the x has to be log base 6. So we're going to apply a logarithm on both sides. We're going to say log base 6 on this side, and we're also going to do log base 6 on that side as well. We know that the log base 6 and the base 6 cancel each other out. We just have x on the left. Log base 6 of 37 is a decimal value, but for now, we're just going to leave that as our answer. Pause it and try and see if you can come up with the answer to this one yourself. Keep in mind that we're going to apply the same process we did. We're going to need to get the exponential by itself. So that 13 has to go first. So it's going to be 8 times 4 to the 6 minus 2x, and that's equal to 28. Then we're going to divide both sides by 8 to get the exponential by itself. And this part here reduces to 7/2. So we're going to have 4 to the 6 minus 2x is equal to 7/2. So how do we get rid of the base 4? Well, remember, we're going to use the inverse, which is a log. So we're going to do log base 4 on both sides. So log base 4 cancels out with base 4, and that just leaves us with 6 minus 2x and whatever log base 4 of 7/2 is. We still need to get x by itself, so let's subtract 6 from both sides of our equation. So now what we know is that negative 2x has the same value as log base 4 of 7/2 minus 6. All we need to do now is just divide by negative 2. So x is going to have a value of whatever you get when you do log base 4 of 7/2 minus 6 and divide that by negative 2.